Hello, everyone. This is Yue Gao from Microsoft Research. I am here to introduce our latest work, Implicit Motion Function. Firstly, let's discuss the introduction part. Recent advancements in video modeling extensively rely on optical flow to represent the relationships across frames, but this approach often lacks efficiency and fails to model the probability of the intrinsic motion of objects. The optical flow has inherent limitations. It lacks sparsity, captures only the positional change of pixels, and fails to model the probabilistic aspects of object movements. In addition, conventional encoder-decoder frameworks model the correlation in the encoder, leading to limited generative capabilities and redundant intermediate representations. Therefore, the non-editability and rigid structure of explicit optical flow present significant challenges in video generation tasks. The integration of sophisticated neural networks is necessary for downstream generation tasks. In implementing the IMF, two primary challenges emerge. The first concerns defining and extracting sparse tokens. Our approach circumvents this limitation by allowing the encoder to extract latent tokens without tying them to physical coordinates, preserving semantic integrity while maintaining sparsity. The second challenge involves modeling correlations with latent tokens. We model frame relationships and align reference appearance features to the current frame using a latent token decoder to generate motion feature maps from compact latent tokens and processing these features through cross-attention. Our contributions can be summarized as follows. Propose the implicit motion function, a novel framework for video modeling at extremely low bit rates and high-quality video generation. Incorporate the latent token decoder and the implicit motion alignment as the implicit motion function for correlation modeling. By manipulating the latent tokens, the proposed method can achieve high-quality editing results for talking head images. Next, let's talk about the method. Here's the overview of our method, which is encoder-decoder style. The encoder contains the dense feature encoder, EF, and the latent token encoder, ET. The decoder is composed of several implicit motion function, IMF blocks, and the frame decoder, DF. Given a reference frame XR, the dense feature encoder, EF, extracts multiscale feature FR-QUEL. The latent token encoder, ET, encodes the reference frame and the current frame to TR and TC independently, with the latent token TR and the appearance feature FR extracted from the reference frame. The target of IMF is to obtain the appearance feature FC of the current frame from its latent token TC. Specifically, the IMF is mainly composed of two parts. First, we design a latent token decoder, IMFD module, to transform the highly compact latent tokens into spatially aligned motion features that correspond with the frame. Subsequently, we utilize the implicit motion alignment, IMFA module, to align and refine the appearance feature of the reference frame to the current frame. After the latent space is trained, we can edit learn tokens through another independent token manipulation network. Now let's talk about experiments. Here are some settings for the experiments. Table 1 and Table 2 show the quantitative comparisons with previous SOTA models. These results show that our method significantly outperforms previous SOTA methods. For talking head data, although previous methods can approximately reconstruct the correct facial area, only our model accurately reconstructs the non-facial areas. Our model also performs best for local motion changes, like blinking. For general data, our method is able to precisely reconstruct various contents with complex motion, such as blooming. However, the methods based on explicit representation and alignment perform poorly in cases of drastic content changes and have inferior modeling capabilities for subtle motions, such as minor positional changes in leaves and flowers. The rate distortion curves show that our method is significantly better than all previous methods in terms of rate distortion trade-off. We compare previous SOTA explicit methods on both talking head and general datasets. The results demonstrate our implicit model's superiority. Token editing results demonstrate that our method not only parallels the editing performance of PECHED, but also surpasses it in terms of realism and naturalness. The ablation results indicate that explicit representation performs poorly for hands and other complex motion. Reference frame selection greatly impacts reconstruction quality, with closer frames typically improving results. The attention visualization shows our IMF effectively discerns the correlation between two frames and identifies new elements. Finally, let's draw a conclusion. This paper introduces the implicit motion function, an innovative approach that advances beyond traditional optical flow in video modeling and generation. The implicit methodology not only achieves high-fidelity video reconstruction, but also demonstrates a remarkable compression ratio improvement. Its capacity for directly editable latent tokens paves the way for superior editing performance. We believe IMF represents a meaningful step forward in video modeling. Thanks.